Hello and welcome to this lecture on LDPC codes. Okay, so from this week onwards, we will start looking at low density parity check codes. In particular, how the low density parity check codes are specified in the 5G standard. We will only use those codes, and then also how to decode them. We will build up the decoder slowly, and the decoder for LDPC codes has two important ingredients. The overall decoder is made up of two smaller decoders used repeatedly and combined in an interesting way. So the basic decoders that are used in the LDPC decoder is the decoder for a single parity check code and a decoder for the repetition code. Okay, so we have seen the repetition code in some detail. We have not talked about the single parity check code that much. I will talk about it in this first lecture, and in particular there is a way to decode both these codes which are both simple and at the same time a little bit different from what we have seen so far. So this lecture mainly I am going to focus on these two codes, the repetition code and the single parity check code, and how to build this simple decoder for both of them. Okay, so let me start with the repetition code. Okay, so in particular I will take the 3,1 repetition code, okay, and we will look at it with BPSK modulation over AWGN as we have been doing so far, and I will talk about a slightly different decoder. It's sort of similar to the ML decoder, it does not do very different from that, but we will think about it a bit differently, that is all. Okay, so let us get started. So how does this work? Once again, you have a message bit M. Okay, it goes through the encoder. You produce a code word which is M. Okay, so this is 3 bits. Then you do BPSK. We all know what it is by now, 0 to +1, 1 to -1, and you get a symbol vector S. Okay, and then this goes through noise, and you get a received vector R, which is R1, R2, R3. Okay, and the decoder has the task of producing M hat or C hat. Okay, so what we will consider in this lecture is a soft in, soft out decoder. Okay, so this is the first modification in our decoder. So what do I mean by soft in? We already saw soft decoders before, which take in the real value R1, R2, R3 and then produce a output, but their output was only M hat, right? So traditionally we have been thinking of the decoder as putting out M hat. This is a hard output. Okay, so it tells you what the estimated bit was. Okay, so we will not be interested in M hat in this soft output decoder. We will be interested in some sort of a probability as the output. Okay, a probability or belief, or there are various words that people use for the soft output. Not only do I want to say what the bit is, but I also want to say how much do I believe in that value for that bit. Okay, so that is the idea behind this decoder. So this is hard output. We will not be considering that in this. What we will want here is a soft output. So what I will put out here is L1, L2, L3. Okay, there are 3 real values that will come out of this decoder. Okay, what are each of these values? Li is let us say belief. I will put this in quotes here. I will define it a bit more precisely later on. Belief that bit Ci is, let us say, 0. Okay, so I want some soft output, some real values to come out. Okay, and that is this definition of Li, and I want to say that for each of the bits L1, L2, L3, what's my belief that the first bit is 0, what's the belief that the second bit is 0, what's the belief that the third bit is 0. So actually for the repetition code, it will turn out that all the 3 values are the same. So eventually you will get the same value for all 3, and it does make sense, but you will see there are some subtleties in this. Okay. So let me motivate this with some examples. Okay. So it's always good to look at examples. So example, I'll focus on the decoder. Let's say your R was, let me take a simple little example here, 3 to, and maybe I'll take it as real numbers just to look a little bit more, 2.4, 4.3. Okay. So I get 3 values, all 3 are positive and all 3 are fairly large. Okay. So if you look at it for a while, it's clear what these values are. So once again, remember what is the line here. So we have this transmission which is either +1 or -1, and noise gets added, and what I am receiving here, these 3.1, 2.4, 4.3 are all way out here, right. So these are the 3 received values. Okay. So now what does this 3.1 represent? Okay. So the fact that it's 3.1 means I have a certain soft input about what that first bit could have been. Okay. I transmitted the first symbol, which could have been +1 or -1, and I received a 3.1. Okay. So let's say it's here 3.1. Okay. So if you look at 3.1 and you've received 3.1, it's very likely that the transmitted symbol was +1. Okay. So your belief that the transmitted symbol is +1 is very high. Okay. Same thing with 2.4. So you've got 2.4, it's somewhere here. You really believe that the transmitted symbol is +1. And you also have 4.3, and that's way out here, and that's also a very strong indicator that the transmitted symbol was +1. Okay. So you're quite confident about that. On the other hand, let's look at another possibility here. Maybe R is 0.01, right, -2.2, and then maybe -0.5. Okay. So this is another case here, and let me draw that same line once again here, and you'll see what's going on here is slightly different. So you have +1, -1. You got something really close to 0. So this is 0.1, 0.01. Okay, it's really close to 0. Then you got something far away, and then something intermediate. Okay. So now if you look at 0.01, okay, it's really, I mean, of course, if you do a hard threshold, you're going to say the transmitted symbol was +1. Okay. The hard threshold will go towards this. This is strictly closer. Okay. But my confidence in saying that the transmitted symbol was +1 is not very high. Just looking at 0.01, it's not very high. Okay. So I don't know whether it was +1 or -1 because it's just 0.01 off. Okay. So in that sense, 0.01 also represents a belief about first bit based on R1 alone, right. Okay. You received R1, that was 0.01. So if I'm not given any other information, that's the best belief I have. Okay. On the other hand, if you think about it once again very carefully, the same bit was transmitted 3 times, right. The same bit was transmitted once again, and I got -2.2, which means if I've received it here, my belief is quite strong about what the transmitted symbol could have been. It has to go to this guy. Okay. So this is a strong belief. Okay. Really, it couldn't have been +1. It wouldn't have had such a huge noise. Okay. The noise is most likely to have been -1. Okay. The probabilities work that way. Remember, the Gaussian falls exponentially. So as you go farther away, the probabilities really drop significantly. So -2.2 is a very strong indicator that it's -1. And remember, from my code, I know that I transmitted the same bit once again. Okay. So to find a belief about the first bit, not only should I use R1, I should also use R2 and even R3. Okay. So now R3, you might say -0.5 is not as strong as -2.2. It's a little bit weaker than -2.2. It says it's -1. It's much better than 0.01, but still it could have been +1 also. I mean, it's not so far away from +1. Okay. But nevertheless, it is still a stronger belief than 0.01. Okay. So, when you want to decide about the first bit, you want to take into account R1, but also what R2 and R3 tell you about the first bit, okay, particularly because the same bit was transmitted again and again and again. This is a repetition code. If the bit was 0, you transmitted +1, +1, +1. If the bit was 1, you transmitted -1, -1, -1, and all three were received for that. Okay. So, you want to use R1 as well as R2 and R3 to compute the belief for the first bit. Okay. So, in other words, if you just look at these examples, it is clear that you compute L1 R1, R2 and R3. Okay. R1 tells you directly what it is for the first bit, but then the second bit and third bit are also the same. So, you need to figure out how to combine R1 and R2 and R3 to tell you about L1. Okay. So, now how to do this combination? There is lots of intuition that one could use and maybe directly decide. It turns out, I will give you the answer first and then I will tell you how to derive this. So, it turns out the correct way to compute this is L1 equals R1 plus R2 plus R3. Maybe I will put, you might want to scale it with something. Okay. You multiply by some factor. Okay. So, theoretically putting that factor there is good, but in practice people just ignore this factor. Okay. So, ignored in practice. So, you can just say R1 plus R2 plus R3. You do not lose much by that factor, it is a positive factor. Okay. So, you do not lose much by ignoring that factor. Okay. So, this is the answer, and this is the actual computation that you have to do to find out the total belief about the first bit based on R1 and R2 and R3. All three of them are being used. So, if you look at it, it has two components. One is what is called intrinsic, these two is what are called extrinsic. Okay. So, once again, like I said, we will completely ignore this factor, we will not use this at all, we will only use R1 plus R2 plus R3. Okay. And even that, there are two components. One is the intrinsic belief that you have based on what you received for that symbol R1 directly, and then extrinsic, what comes from R2 and R3. And why do I have to add these three? One can do a small probabilistic derivation here. I am going to do it very quickly, but the moral of the story is you can see intrinsically, I mean you can see intuitively why this is R1 plus R2 plus R3, right. So, the same bit was transmitted 3 times. So, you are allowed to add the 3 received values to get the total belief for every bit. In fact, this is the same for L2 also, and L3 is also the same, okay, except that the intrinsic and extrinsic will differ, right. So, if you look at L2, you have R1 plus R2 plus R3, okay. So, this is the intrinsic part, these two are the extrinsic part, okay. Likewise, for L3, R3 will be the intrinsic part, R1 plus R2 will be the extrinsic part. So, what is intrinsic and what extrinsic changes in L2 and L3, but the overall expression is the same, R1 plus R2 plus R3. Okay. So, this is an example of a soft in soft out decoder for the repetition code. Okay. So, the soft in soft out decoder puts out 3 real values, okay, intrinsic plus extrinsic. This intrinsic extrinsic division is quite important. Okay. So, the intrinsic one is what you receive from the channel corresponding to that particular symbol. The extrinsic is what you gain or glean out of the other received values about this particular symbol. Okay. So, I am going to do a quick derivation here to show you how this comes from. The main idea is this notion of a log likelihood ratio. Okay. So, once again I want to briefly comment, if you go back and look at this decoder, those of you who have implemented the ML decoder for repetition code and have seen it will quickly recognize this R1 plus R2 plus R3 also showed up in the ML decoder, and this is exactly like the ML decoder. Okay. So, what is it that we are doing which is different? Okay. So, what is different about this soft output? At this point it is not very apparent. For this code it is not very obvious. It seems like a like an unnecessary thing we are doing, putting out soft output. Okay, but when we combine this as part of the LDPC decoder, you will see where this intuition for addition will come from. Okay, so I'll play on this a little bit later on as well, but for now let's see a quick definition involving log likelihood ratios and all that. Okay, so once again, so this is how log likelihood ratio is defined. So supposing I want to ask this question. So the probability that C1 equals 0 given R1. Okay, so remember once again, what is the setting here? The setting is this C1, C2, C3, right? C is C1, C2, C3. The same 3 bits were transmitted again and again. Now I want to look at R1 and ask the question, what is the probability that C1 was 0 given R1? Okay, so for this you can do this little computation using Bayes rule. You will see that this will be the PDF of R1 given C1 is 0 times the probability that C1 is 0 divided by the PDF of R1. Okay, the density of the received value evaluated at R1. Okay, so this is easy enough to write. Now this is the prior probability, and it's equal to half. Okay, why is that? C1 is the message itself. It could be 0 or 1 with uniform probability. Okay, now one can also, so this is a calculation you can do. Actually, you can write down what the density will be given C1 is 0 and what is the density of the total density, etc., and find this out. But usually people use something else here. They use this likelihood ratio. So let me write down what that is. You can also write down what's the probability of C1 is 1 given R1. This will be sort of similar to this. Okay, so once again, this is also a prior probability and it's 1. Okay, and it's comfortable to take this ratio here. It gets rid of some of the quantities that you don't really care too much about. Okay, and you notice under this assumption of half probability, I simply get the ratio of the likelihoods. Okay, so this is the posterior probabilities and this is the ratio of the likelihood. Okay, so this is called a likelihood ratio. Okay, and one can compute this quite nicely. Okay, so remember, if C1 is 0, implies the symbol is +1, okay, and R1 is 1 plus normal 0 sigma squared. If C1 is 1, the symbol is -1 and R1 is -1 plus normal 0 sigma squared. Okay, so this ratio will work out as 1 by root 2 pi sigma. This is the normal density. With mean on the numerator, you will have a mean of +1, R1 -1 whole squared by 2 sigma squared, divided by, for the denominator, you will have e power R1 +1 whole squared by 2 sigma squared. Okay, so one can simplify this. I am going to skip the simplification a little bit. You will get overall e power 2 R1 by sigma squared. Okay, so this is the likelihood ratio, probability of C1 equals 0 given R1 divided by probability of C1 equals 1 given R1. Okay, the log of this is called the log likelihood ratio. And that you can see will work out as 2 by sigma squared times R1. Okay, so this is the log likelihood ratio, and this is the intrinsic LLR. Okay, so you can see it's proportional to R1. This is R1 into a positive factor. Okay, R1 is the most critical component. 2 by sigma square actually depends on the channel value. If sigma is the channel noise variance, if it is small, 2 by sigma square is going to become very large. So at high SNR, this factor will be very large. At low SNRs, when sigma has 1 or 2 or value like that, then the factor is very small. Okay, but nevertheless, it's a positive factor, and in most cases, we will usually ignore this factor. Okay, we will use just R1 to represent this LLR. Okay, so this intrinsic LLR is sort of the belief. Okay, this is the belief that we spoke about. Okay, so this is just intrinsic LLR. It's also referred to as the channel LLR or input LLR. Okay, so this is something important to remember. So now, whatever your modulation scheme may be, whatever your channel may be, okay, you have, when you use an LDPC code on that channel, maybe you are doing 64 QAM instead of BPSK. Maybe you have some other channel like a ISI channel or something else, you are doing OFDM, whatever it is you are doing, you may have some other factors in there. The first step before using the LDPC decoder or any other soft-in software decoder is to compute the intrinsic log likelihood ratio or the channel log likelihood ratio for a particular bit. Okay, so this will be the first block that will come in. In our case, we have just BPSK AWG and it's a very simple model. The input LLR is simply proportional to the received value. Okay, so it's proportional to R1. Okay, so same thing will happen for R2 as well. C2 probability of C2 equals 0 given R1 divided by probability of C2 equals 1 given R1 will also be probability of C2 equals 0 given R2 divided by probability of C2 equals 1 given R2 will be 2 by sigma square times R2. Okay, so sometimes I like to call this a small L1. Okay, so likewise L2, which is let me write this down just for L2 alone, probability of C2 equals 0 given R2 divided by probability of C2 equals 1 given R2 will also work out as 2 by sigma squared times R2. Okay, so this same thing for L3 as well, one can write down an expression for L3. Okay, so this is input log likelihood ratio. Now, like I said, I am interested in a final belief which is a combination of all the three received values. Okay, so for that, what I need to do is the following. Okay, so output LLR, okay, in my SISO decoder. Okay, so this capital Li is actually the log of probability of Ci equals 0 given R1, R2, R3, all the three received values divided by probability of Ci equals 1 given R1, R2, R3. All the three received values have to be taken into account. This is the output LLR. This is what I really want at the output. What is my final belief after having seen all the three received values? So, if you looked at the previous calculation, it was the channel LLR or the intrinsic LLR. This is the output LLR, which is the final belief after I have seen all the three received values. Okay, so I am going to compute L1 first. You will see the computation of L1 is quite simple. Everything starts once again with probability of C1 equals 0 given R1, R2, R3. You will notice once again using Bayes rule that this is the joint density given C1 is 0 times the probability of C1 is 0 divided by the overall joint density. So, once again this is 1/2 equal probability assumption. Likewise, you can also write probability of C1 is 1 given R2, R3, R1, R2, R3. This will be f of R1, R2, R3 given C1 is 1 times probability of C1 is 1 divided by f of R1, R2, R3. Okay, so this is for the repetition code a fairly simple computation. If you take the ratio, you get probability of C1 equals 0 given R1, R2, R3 divided by probability of C1 is 1 given R1, R2, R3 is simply the likelihood ratio, right. So, it turns out for the repetition code, this conditional joint distribution, conditional joint density is easy to write down. Okay, so the repetition code makes that very easy. Let me show you how that's done. C1 equals 0 implies symbol vector is +1, +1, +1. So, that implies R1 equals 1 plus normal 0 sigma squared. Okay, so, I will put N1 here. R2 is 1 plus N2 0 sigma squared. R3 is 1 plus N3 0 sigma squared, and N1, N2, N3 are independent. Okay. Something similar happens when C1 is plus 1, the symbol vector is -1, -1, -1, and R1, R2, R3 are -1 plus 1 normal distribution, -1 plus another normal distribution, -1 plus another normal distributed value. All three are independent because different bits go through independent realizations of the channel. So, once you know this, once you know what happens when C1 is 0 and C1 is 1, you can plug in the normal distributions here. So, this is independent, conditional on C1 equals 0, these three values are independent. So, you can factor the things and multiply out and write down as a product. So, let me do that for you here. Okay. So, my probability of C1 equals 0 given R1, R2, R3 divided by probability of C1 equals 1 given R1, R2, R3 is going to be, there will be some 1 by root 2 pi sigma which will cancel on both sides. So, I am not going to write down that part, I will simply write down what happens in the e power term, okay, minus R1 minus 1 whole squared by 2 sigma squared e power minus R2 minus 1 whole squared by 2 sigma squared e power minus R3 minus 1 whole squared by 2 sigma squared divided by e power minus R1 plus 1 whole squared by 2 sigma squared e power minus R2 plus 1 whole squared by 2 sigma squared e power R2 plus 1 whole squared by 2 sigma squared. Okay. All right. So, that was easy enough. So, notice what happened here, the way in which the code words are set up is quite important here, that is why this happened. You can do a lot of simplification, cancelling, etc., etc., etc. You will finally get 2 by sigma squared times R1 plus, oh, sorry, forgot the e power here. You will get e power, a lot of things will cancel, you will get e power 2 by sigma squared times R1 plus R2 plus R3. Okay. So, if you take log on both sides, I will get L1 to be 2 by sigma squared, or maybe I will write the 2 by sigma square on the other side because it is a positive factor, it does not affect too much. You get R1 plus R2 plus R3 times 2 by sigma squared. Okay. So, clearly you can identify the extrinsic and intrinsic parts now. This is the intrinsic, these two are extrinsic. Okay. So, go back and look at what I did, and if you want to change, instead of L1, if you want to put L2, you will get exactly the same calculation. Okay. So, you will see nothing will change, eventually L2 will also become the same thing. Okay. So, finally, one can write down that Li can be taken to be R1 plus R2 plus R3 times some positive factor, which we will, like I said, we will set it as 1. Okay. So, we do not bother about that positive factor. If you want exact log likelihood ratio, you have to incorporate that, but that is not usually that is not very relevant. All you need to do is find out this capital Li. Okay. So, like I said, Li is the same for the repetition code, simply add the 3 guys. It changes, intrinsic and extrinsic changes, but nevertheless it is the same. Okay. So, we did a quick derivation here, and we saw how to do soft in, soft out decoding for the repetition code, how to put out 3 values and find out soft output for the repetition code. Hopefully, this was easy enough. I am not going to show you the MATLAB code for this at this point. Maybe I won't do it. Maybe later on we will see that. Okay. But what is more important is the single parity check code as well. Okay. So, this is the repetition code. We started with that. Hopefully, this is clear. The next lecture, we will move on to the single parity check code, and we will see how to repeat the same thing for the single parity check code. That involves a slightly more complex calculation, but we will do that. And then after that, we will write MATLAB code for maybe both the single parity check code and the repetition code. Okay. So, like I said, these two simple decoders are important ingredients in the decoding of LDPC codes. They will play a very important role. We will see that later. Okay. So, we will stop here for this lecture. We will pick up with the single parity check code in the next one.